right, just when you thought we must be done with the double angle identities, we have a little bit more to talk about. The results of this video are actually quite useful in higher level math, particularly calculus 2 and 3. So it actually is a neat result of the double angle identities. All right, let's dive in. So although the last video showed us how to use double angle identities to find values for sine of 2 theta or cosine 2 theta given different information, this is going to focus more on a rewrite of the identity. And we've seen that happen already a little bit in this trig aspect of precalculus. So we use these sum identities to arrive at these three forms of cosine 2 theta, as well as at this form of sine of 2 theta. So this process will feel slightly similar to that. What we're about to embark on is something called, in some classes, the reduction formulas. They go by different names, but basically the point is the same. And that is, we are going to take the double angle identity for cosine and select one of its forms, of which there are three, to rewrite it for another term, right? So as a quick analogy, I'll use the space over here. We know from the past that area is equal to length times width. And we often know the length and width of a room, and we just multiply the dimensions to find the area. But we also know we can take this formula and rewrite it or solve it for L or W, right? So for example, if I were to divide both sides by L, that would allow me to that would allow me to solve for W. So this would allow us to state that area divided by length is equal to W. So kind of a similar idea is happening here. We are going to use one of the double angle identities for cosine to solve for sine squared. So noticing these three different forms for cosine of 2 theta, we're going to go ahead and pick on the form that only involves sine squared and cosine of 2 theta. So that's going to be the third form. So I'm going to go ahead and write what that third form states, which is that cosine of 2 theta is the same as 1 minus 2 sine squared theta. Alright, and we've seen this. We actually used this identity in the last video since we were given information about sine. All we're going to do here is solve for sine squared. So that means we need to start pulling away all the other pieces through careful operations of addition or subtraction and or multiplication or division. So if the goal right now is to solve for sine squared, it looks like a good first step would simply be to subtract 1 from both sides. So I'm going to go ahead and say cosine of 2 theta minus 1 will equal now to negative 2 sine squared theta. So what we've done is subtract 1 over, and now a next step following some algebra would be to divide both sides by negative 2, knowing again that our goal is to get sine squared alone. So at this point, the way we write it will vary from person to person, but I'm going to go ahead and pull out the 1/2. So dividing by 2, this 2 on the bottom here, is the same as timesing by 1/2, but the 2 we had on the bottom was negative, so that's going to make the term inside, which was positive cosine, that'll make it negative, and then a negative 1 divided by a negative 2, that'll make this next term positive. And then on the right hand side, we freed up what we were trying to solve for, which was just the sine squared term. So I'll take one more step to rewrite the reduction formula in a slightly more common way. I'm going to place the sine squared we were tasked to solve for on the left, and on the right I'm going to state it as 1/2 the quantity, and I'll put inside the positive 1 first and then the negative cosine of 2 theta second. And there we have it. So this will be the reduction formula for sine squared theta. It's actually very, 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 very useful. We're going to do the same process on the next slide, except for we're going to swap out this sine squared for a cosine squared. It's a very similar process. Okay, so now we're going to solve for cosine squared. we know again that there are three different forms for the identity of cosine 2 theta. I want to pick the form that only involves cosine squared, since that's what we're solving for. So I'm going to pick on the second form that we see in the box here. So jotting down that form, this states that cosine of 2 theta is the same as 2 cosine squared theta minus 1. And we'll move through a couple algebraic steps to isolate cosine squared. So if the steps we took in this first example weren't too clear, maybe going through the process in a very similar example will help clarify. Alright, so if our goal is to isolate cosine squared, it looks like a good starting point would be to add 1 to both sides. So that'll tell me that cosine 2 theta plus 1 is equal to 2 cosine squared theta. It looks like just one more step is required to isolate cosine squared. Since it's being multiplied by 2, we'll divide by 2. That was needed on the right, so of course we'll do the same thing to the left. And the next couple steps will vary by person, but I'm going to try to make them look a certain way, just so that you're familiar with them down the road for those of you who take Calc 2 and 3. So it's common, as we saw in the last one, to pull out dividing by 2 as timesing by 1/2. So we have half of cosine 2 theta plus 1 equaling the cosine squared theta we were trying to solve for. The only rewrite I'm going to do is I'm going to place the cosine squared on the left, and when I write 1/2 of the parentheses, I'm just going to reorder the terms in there to make it match the order of our last one. So I'm going to put the 1 first and then the positive cosine 2 theta at the end. So this is now what we can take moving forward as a rewrite for cosine squared of theta. Take a quick peek at these two end results and how similar they are. Sine squared theta was half of 1 minus cosine 2 theta, whereas cosine squared theta is the same thing except for this sign in the middle changed to a positive. So you don't have to commit these to memory, though if you take more math you likely will, but that is one important distinction. It's just the sign in between that changes. So as with everything else we've done so far today, I'm sure you want to see how this could be used, so we'll end this video by looking at that. So here's an example where we're asked to rewrite the expression cosine squared times sine to the 4th with no powers. It's a little harder than you might think, but we're going to utilize the results from earlier on in the video. So remember that earlier we saw cosine squared is the same as this quantity here, and sine squared is the same as this quantity here. So you might want to jot those down as we're going to use them in this example. So sine squared is 1/2 the quantity 1 minus cosine 2 theta. Cosine squared is very, very similar. It's equal to 1/2 the quantity 1 plus cosine 2 theta. Alright, and I'll be writing them on the next slide as well. One thing that we should immediately also consider is we notice this power of 4, but we're only using what we just learned. So I'm going to go ahead and take cosine squared and sine to the 4th, and I'm going to break sine to the 4th in 2 pieces. Make sure you agree that sine to the 4th is the same as sine squared times sine squared. So if we were to multiply those back together, we'd still get back to the power of 4. The reason it's really helpful to write it in that way is because the identities we just discussed involved squared terms rather than powers of 4. Alright, so anytime we see a cosine squared of theta, we can now rewrite that as 1/2 the quantity 1 plus cosine 2 theta. Anytime we see a sine squared term, we can write it as almost the same, just that sign in between changes to a minus. And we've got one additional sine squared term here, so we'll also rewrite that one in the same way I just wrote that green term, so 1/2 1 minus cosine 2 theta. Now you might feel like we're done because the directions did just state to rewrite the expression with no powers. But if we were to actually FOIL this, we would end up with more powers, so we got to keep going a little bit. So let's start by at least getting all these fractions out front so that they don't interfere too much. A half times a half times a half means we can pull out 1/8. And I'll go ahead and multiply the 1 plus cosine 2 theta by the 1 minus cosine 2 theta. And if we go ahead and multiply by FOILing, I would get 1, and then my next term would be a negative cosine cosine 2 theta. Then I would get a positive cosine 2 theta, and my last term would be a negative cosine squared 2 theta. So just to recap, I'm taking this red parentheses and FOILing it with this green parentheses. So 1 times 1, 1 times negative cosine 2 theta, cosine 2 theta times 1, cosine 2 theta times negative cosine 2 theta. So just make sure you agree with those terms there. And then I'm going to leave the purple parentheses alone for now. Let's just clean up what's inside our blue parentheses. So looks like we got 2 terms in the middle that are the same but opposite. And that's because it was a difference of square structure. So it's actually something you may have known before actually FOILing. But I'll go ahead and just cancel out these 2 terms in the middle, the negative cosine 2 theta and the positive cosine 2 theta. And I'll go ahead and write this as 1 minus cosine squared 2 theta. Okay, and that's still multiplied again by the 1 minus cosine 2 theta. So maybe at this point we could go ahead and FOIL again. The order in which you do this doesn't necessarily matter. So some folks are going to tell me that they want to use the identity again right away here. But let's go ahead and just FOIL it out. Alright, so if we keep multiplying, basically we're going to start off again with the 1 times the 1, so that'll give us a first term of 1. Then we'll do 1 times negative cosine 2 theta, which gives us negative cosine 2 theta. Then we're multiplying negative cosine squared of 2 theta times 1. That sounds like negative cosine squared of 2 theta. And last, we get a negative cosine 2 theta times a negative cosine 2 theta, which sounds like a positive cosine cubed of 2 theta. I'm going to go ahead and leave it as cosine 2 theta times cosine squared of 2 theta, because the identities that we know allow us to rewrite squared terms, not cubed terms. Alright, so I hope so far in terms of just the FOILing process, that multiplication process, we feel okay. I know sometimes FOILing with trig functions is a little weird at first. We're not always quite sure how to deal with the exponents. So make sure you agree with those terms. And then what I'm going to continue doing is just apply the identity again. So you can tell at this stage we're not done because we still have exponents, particularly right here, and then again right here. So we need to utilize the reduction formulas again. Alright, so here we go. I'll carry down the 1 minus cosine 2 theta. There's nothing that's needed to be done on those terms. But when we hit this cosine squared of 2 theta, I'm going to go ahead and apply the reduction formula again to get 1/2 the quantity 1 plus cosine of twice the angle, where the angle is already 2 theta. So the new angle becomes 4 theta. And then I'll go ahead and write down the plus cosine 2 theta. And then we bump into another opportunity to utilize that cosine squared definition. So in place of cosine squared 2 theta, again, we'll put 1/2 the quantity 1 plus cosine of double the angle, where double 2 theta becomes 4 theta. All right, so in terms of utilizing the identities, we're actually done. Some of you may say, can we be done for good? And just looking at the problem a little bit, I mean, we have done what the problem asked us to do, but I'm just going to take a few more steps because it looks like we could clean up a little bit. So we're almost there. But let's go ahead and do just a tad more cleanup. This is good to be patient with the process. So let's see, I'm going to apply this negative. This 1/2 times 1 is 1/2, but it's going to drop down as a negative 1/2. Half times cosine 4 theta is half cosine 4 theta, but it'll be a negative. And then we've got, let's see, 1/2 times 1, which is a half, times by cosine 2 theta. So we've got a half cosine 2 theta. And then we've got a half cosine of 2 theta times cosine of 4 theta. So there's kind of a little bit of weird distribution going on there. So it's basically half cosine 2 theta times 1, half cosine 2 theta times cosine 4 theta. Alright, so again, it's looking pretty good. We can collect a couple like terms inside before we truly call it quits. So I'll keep carrying down this 1/8. Within the parentheses, maybe I'll go ahead and work on first the plus 1 and the minus 1/2. 1 minus 1/2 makes 1/2. I'm going to see if I can find any like terms with my negative cosine 2 theta. I see one down the road here as a positive 1/2 cosine 2 theta. So negative 1 cosine 2 theta plus 1/2 cosine 2 theta leaves us with negative 1/2 cosine 2 theta. I don't see any other terms that involve just a cosine 4 theta, so I'm going to drop that down as a negative 1/2 cosine 4 theta. And similarly, this last term at the end did not have any like terms, so it's going to drop down as a plus 1/2 cosine 2 theta cosine 4 theta. At this stage, you notice each term within the parentheses has a factor of 1/2, it looks like. So we could factor that out as well. Or we could also distribute the 1/8 into all the terms. Let's go ahead and call it quits there. That was a little bit of an exhausting process. So not a huge deal in pre-calc, but the use of these identities will become really helpful in the context of calculus. The reason they become helpful in calculus is they can allow us to transform problems that we don't know how to solve into simpler pieces. And that's just something that's pretty foundational to mathematics in general. So hopefully that makes a bit of sense. I think that's it now for double angle identities.